Hello, hi to everyone. Welcome back to chapter number 4, logic gates. Okay, first of all, see the definition of logic gate. You know, logic gate is a electronic circuit. Okay, so in the case of logic gates, we have a one output. Okay, and more one or more inputs. So only one output is present, one or more inputs are present for the logic gates. We'll see what exactly the gates are present. The output signal appears only certain combination of input signal. For example, you are given the two inputs A and B. This particular combination will get the some particular output. Maybe C is the output. So here different type of combination will take the different type of inputs, outputs we are going to take. Next one, logic gates are basic building for the many digital systems. Maybe in case of any electronic circuit, we are taking ICs are present. That is based on these logic gates building blocks only. Okay. Next one, they implemented the hardware logic functions. Yes, on the basis of local algebra developed by George Boole. Based on the Boolean algebra, we are going to develop the hardware logic functions. Okay, already in your chapter number 5 we explained linear algebra, Boolean algebra basics, right? Next, the unique characteristics of Boolean algebra is that only one or zero, only two parameters, two values are present. The first one is a 0, second one is a 1. Only two values are only present. That is the only unique feature of the Boolean algebra, either 0 or 1. Okay, variables. So these gates are available in today various IC families. In your 6th chapter we are going to discuss the different ICs. In that, the popular IC families are TTL logic, transistor logic, and ECL, that means emitter coupled logic. Next, metal oxide semiconductor, MOS logic, and complementary metal oxide semiconductor, CMOS logic. So all these logics are related to the chapter number 6. Complete discussion will be there. So these are the ICs available. Okay, next, in this particular chapter we are going to discuss about AND gate, OR gate, NOT gate, NOR gate, NAND gate, and exclusive OR gate, that is called as XOR gate, with their truth tables. We are going to discuss in detail everything. Okay, now before moving to the OR gate, I am going to give some important points here: positive and negative logic. Okay, so positive and negative logic I will explain here. The number symbol 0 and 1 represented in computing system. So it is a possible states. 0 and 1 are possible states in the computer system. In these possible states, it makes no difference if these two states are referred to as a on and off. That means closed and open, that is equivalent, or high and low, or plus and minus, true or false. All of you following? So this particular 1 and 0, can be represented like we can use it as a on and off. That is called as on is nothing but a 1, off is nothing but a 0. Closed and open, closed is nothing but a 1, open is nothing but a 0. And then high and low, high is nothing but a 1, low is nothing but a 0. Plus and minus, plus is nothing but a 1, 0 is nothing but a minus. Likewise, true is 1, false is 0. So based on that, okay, clear? Now we have two logics. Those logics are positive logic and negative logic. Okay, on the negative logic. So throughout our lecture, until unless they mention in the examination, you should consider only positive logic. All of you got my point? Until unless mention in the examination, you choose the negative logic, then only you consider negative logic. Otherwise, in the any question you are considered in the objective examination, where you are attending the examination, only positive case. Well, we will see what are the positive logic. Okay, so in the positive logic, 1 one represented on circuit, closed switch, and high voltage, and a plus sign, and a true statement. True is called as a statement. In this, all these logic, one represented on, close, high, and plus, and true if you are considered as a 1, that is called as a positive logic. Okay, coming to the 0. 0 represented here off state, open, low, minus, and false. This terminology is present in the positive logic. It is represented by the 0. Okay, this is a quite reverse, opposite to these conditions. This is called as a negative logic. In the negative logic, this 1 is represented as a off, open, low, minus, false. Opposite to that, 0 represented on, closed, high, plus, and true. Got my point? So this is about the positive and negative logic. Final conclusion here: whenever positive logic, 1 represented all the active conditions, 0 represented all the deactive, like is off state conditions. Okay. Next, we are start with the OR gate. It is one of the important gate. So in the OR gate, we are going to discuss in the different configuration. The first one is using switches, second one is using diodes, third one is using transistors. In your syllabus, in detail mention all 3 conditions. So we need to learn all 3 conditions, then only can attempt the question. Okay, at least 2 questions from logic circuit, logic families from the previous papers analysis. That means this chapter is a very important chapter. We can spend 1.5 hour time. We can completely study about the logic gates. Okay, next we are moving to the OR gate. This is a representation for OR gate. Okay, this is a symbol. So here OR gate is a function of summation. So A plus B is equal to C. That is a logic. So in that particular logic, A plus B, whenever OR gate is present, plus sign is present, always it is a parallel. Just now I mentioned in the Boolean algebra cases also how to draw the switches, right? So plus OR gate is mentioned as a parallel. So plus, whenever plus is present, it is a parallelly connected. So this is about representation about the switches for the OR gate. Now I will analyze whenever A is 1, okay, B is 0, that means A is closed. So current will be passes from here and then A and then light will be glow. Yes or no? Yes. Even though B is a open circuit, light will be glow. That is the first case. Second, whenever B is on, A is open. In that case also light will be glow. Whenever A is on, B is on, then only also light will be glow. Whenever both are open, there is no path of current flowing through that. That means it is a light will be low, off state. I mentioned in the positive logic, off is nothing but a 0, on is nothing but a 1. So here see, both 0, 0, both are 0, 0. What will happen here? 0. Both are 0 and 1, 1, 1 and 0, 1, and both are on, it is a 1. Clear? This is the truth table for the OR gate. Okay, simply it is you need to remember this particular truth table. You can answer any question from the OR gate. So how exactly the questions will be asked in the examination, we'll see this. These are the points related to the OR gate. We'll see one by one. The OR gate as a one output when either A or B both are 1. This is one of the important statement. Whenever OR gate output is 1, either A or B both are 1, then only OR gate is 1. See here, either A are 1, B are 1. We'll get the 1 only logic. Otherwise, any or all gates, any or all gates are 1. The output occurs any or all inputs are present. So that is a terminology you need to remember. Any or all is related to the OR gate. Okay, very important point. Next one, the output would be 0. Yes, only if both inputs are 0. Yes or no? Yes, output will be 0 whenever both the inputs are 0. Next one, the OR gate represented the Boolean equation, A plus B is equal to C. This is a Boolean expression for OR gate. So the meaning of this equation is C is true, yes, C is true when either A or B is true or both are true. Okay, that were from the truth table. Alternatively, it means that C is 1, either A or B or both are 1. So every statement I mentioned here, very, very important. Okay, the OR gate is equivalent to parallel circuit. It is also important question. The OR gate is equivalent to dash, and then they will give the options: series circuit, parallel circuit, series and parallel circuit, none of the above. You can choose parallel circuit. So OR gate is also called as a inclusive, not exclusive, inclusive OR gate. OR gate, another name is inclusive OR gate, because it includes the case when both the inputs are true. That's why it is an inclusive OR gate. Okay, clear? Next, in the OR gate, you can analysis with the help of the relay. Okay, and this is a circuit you need to remember. This is the relay function. So these both the relays are connected in parallel. So I will explain here. Whenever it is a positive sign, so whenever A is equal to 0, B is equal to 0. For example, there is no activation of relays K1 and K2 are off state. There is no question of output is 0 in the first case. Second one, in the second one, A is equal to 1, B is equal to 0. That means that the K1 attracts the M, right? Whenever it attracts the M, so this 5 volt is present across the C terminal. That means present across resistor. That means C is equivalent to 1. Got my point? Whenever A is a 1, relay is activated. Next, B is 1, A is 0. This relay is not activated, but B is 1, this relay is activated. Whenever this relay is activated, it is attracted, and then whenever this is attracted, this 5 volt, again this 5 volt is connected to this particular R. Present voltage across the C is a voltage across R is a 1. So whenever B is also 1, it is a 1. Got my point? Whenever both are on, both the relays are activated, then this 5 volt appears across this R. That is output terminal across C is equal to F5 plus 5 volt is nothing but a high value, high input value. Whenever high value is represented as a 1. So 1 is nothing but not a 1 volt. 1 is nothing but a logic 1. The 1 may be 5 volt or 10 volt or 20 volt based on the input. But the logic here, high 5 volt, high value 1. 0. Whenever both are open, it is 0. 0 is nothing but 0 volt. We are not connected anything. Okay, got my point. High and low. High is nothing but a maybe 5 volt or 10 volt based on the input. Okay, so everyone got about the relays operation. Next we are moving to the diode combination. This is also important. One of the previous year 2016 question paper, they provided this particular circuit. They are asking to identify the which diagram similar above diagram is related to OR gate, AND gate, NAND gate, NOR gate. They different gates. So it is a OR gate. Always remember, OR gate is a parallelly connected to diodes. It is connected to the resistor. Okay, similar function, A is 0, B is 0, both the diodes are off, voltage across this one is 0, it is a low state. Whenever A is given to the supply, diode 1 is on, voltage across this particular resistor is high. B is on, voltage across resistor is high. Because B is on, it is a conducting. Both are on, both are conducting, both are B is equal to 1. Definitely voltage across the particular resistor is high, it is a 1. Got my point? This is about OR gate. Next, transistor OR gate. So in case of transistors, two transistors Q1 and Q2 connected in parallel, connected to the main circuit. Okay, connected to the main resistor, transistor. Transistor having a 3 states. On state, transistor having a 3 state, that is a cutoff region, saturation region, okay, break. So transistor have a 3 states. The first one is a off state, active region, saturation region. So off state is nothing but a cutoff region. So these 3 particular cases in the unit 3, we are going to discuss about the in detail about the transistors and the diodes concepts. Unit 3 and Unit 4 completely dedicated for the EDC. So we will discuss in detail there. Should remember we have a cutoff and saturation region. Cutoff as well as saturation is nothing but on. These two cases we are using this particular transistor. Okay, let us see. So whenever A is input is given, transistor Q1 is saturated, that is nothing but a Q1 is on. So Q2 is B is 0, Q2 is off state, that is a cutoff region. So whenever A is on, transistor 1 is activated, that Q3 is connected to this particular input. Whenever Q3 is conducting, this particular C output terminal output is available. Okay, got my point. Next, second case. Output is available is nothing but this 5 volt is there now. This 5 volt appears across this particular resistor R2. Okay. Next, second, whenever B is also same thing, whenever AB is operated also same thing, whenever A is equal to 0, B is equal to 0, what will happen here? A is equal to 0, B is equal to 0, both are off state, right? Only, there is no question of conducting Q3. That means the total entire 5 volt drop across this particular R2. There is no question of voltage across this particular output terminal. That is equal to 0. Okay. That is about the logic operation. But you need to remember, but you are not attending the theory examination. For your understanding purpose, I am explaining the working. But you need to practice or you need to remember this particular diagram. They will ask this diagram. Which of the following circuit is represented? The OR gate. They will get the different circuits. You need to identify this particular circuit. Okay. Next, OR gate symbolize of addition. A, B, A plus B. 0 plus 0, 0. 1 plus 0, 1. 0 plus 1, 1. 1 plus 1, 1. But don't consider your carry or something here. Only logic addition only. Okay. This is about the logic gates. Next, OR gate, we are going to consider different cases. OR gate will explain with the help of the OR gate for the different functions. Okay, let us see. 1 plus 1, in case of decimal addition, 1 plus 1 0, 2. In case of binary addition, 1 plus 1 is equal to 0 and 1 carry. 1 plus 1 is equal to 0, 1 carry. 1 carry. So that is a binary addition. But OR addition, 1 plus is equal to 1 plus 1 is equal to 1. There is no carry at all. Got my point? So this particular binary addition in the chapter number 3, we are going to discuss about the binary conversion, binary to decimal, decimal to binary. All this conversion is taking place in the chapter number 3. Okay, we'll discuss there. So see here. Here A is equal to 0, A is equal to 1. This particular OR gate A is equal to 0, right? A plus 1. A plus 1, 1 only. Because A plus 1 is equal to 1. Next, A is equal to 1, here 1. 1 plus 1, 1 only. Yes. So this A plus A is equal to A, not 2A. That means A may be 1 or 2. A plus A is equal to A. This is the first point you need to remember. The second point, A plus 1 is equal to 1. The proof here. For example, A is 0, 0 plus 1, 1. For example, A is 1, 1 plus 1, 1. Even though A is either 1 or 0, you will get the 1 only. That is another point you need to remember. So, irrespective of value of A plus 1 is equal to 1. Next. So, very, very important. Directly, the bits will be there from this particular equations. So, next one. A plus 0 is equal to A. Let us see. For example, A is equal to 0, 0 plus 0, 0. For example, A is equal to 1, 1 plus 0, 1. So here, whenever A value, whatever it may be 0 or 1, the same value appears as A. That means A plus 0 is equal to A only present. Next. Coming to the next one. A plus A is equal to A. Let us see. Both the A and A common symbol. For example, A is equal to 0. 0 plus 0. Both are 0. 0 only. A is equal to 1, both are 1, 1 plus 1, 1 only. That means A, whatever be the A value, the same value appears as the output. That's why A plus A is equal to A. Next, we are moving to the, in case of OR gate, 3 inputs are there. How to write the truth table, we'll see. So this is the truth table for 3 OR gates. So A, B, C and D is the output. 0 plus 0 plus 0, that is 0. So in case of OR logic, any value of input is high, output is high. That's why here any one is high, all are high also, output is high. Right? This is about the truth table. Next, here C, which means that D is 1 when either A, B or C or all are 1. Alternatively, D is true, either A or B, C or is true, all are true. In that particular case, only D is a 1. Okay. Next, we are moving to the exclusive OR gate. You know, inclusive OR gate is nothing but OR gate only. Don't get confused. In OR gate, another name is inclusive OR gate. But exclusive OR gate is different from the OR gate. So, next gate is a very, very important. Exclusive OR gate. Okay. So, what exactly exclusive OR gate? See here. So, this is the representation for exclusive OR gate. That symbol is A plus B is equal to C. This is a representation for exclusive OR gate. That means A exclusive B is equal to C. That is the case of exclusive OR gate. So, I will give the one important. A exclusive B is nothing but everyone remember A bar B plus B bar A. That is for A exclusive B. So, based on that, we are going to form this logic. So, for example, A is 1, automatically B is 0, output is lamp will be glow. For example, A is 0, B is 1, lamp will be glow. So, both are 0 or both are 1, both are 0 or both are 1, lamp will not be glow. That means it is exclusive for common inputs. That is a comparator, you can also call it as a C or truth table. Both are 0, output is 0. Both are 1, output is 1. Either one output is present, output is 1. Either only one output is high, output is only high. So that is exclusive OR gate. So this gate output is 1, either input but not both the inputs are 1. In other words, it has output is 1 when its inputs are different, the output is 0. Then input are the same. When inputs are the same is okay. So finally, whenever this particular point is very, very important in the examination. They will give any statement. It is a possibility is there. Okay. So finally, I conclude that here exclusive OR gate, whenever both the inputs are high or both the inputs are low, output will be low. Remaining all other cases, output will be high. Another way, any one of the output is high, but not both. But not both the inputs, both the inputs are high, output is 1. But very, very important, but not, okay, both the inputs. So next, this logic gate output is 0 when input are either all 0 or 1. Okay, logic gate as output is 0. Whenever output is 0, either all 0 or all 1, then only output is 0. That is why A exclusive B is equal to C. So this circuit is also called as inequality comparator. So there might be chances there. The logic gate also called it as inequality comparator. Which of the logic gate? Exclusive OR gate. It is also called it as a detector because it provides the output only when the two inputs are different. Detector. You can also use it for the detector. So finally, this is about the part 1 video lectures for the OR gate. Okay, next video we are going to discuss the remaining gates. Thank you.